guys. Sorry for the delay. Let's get started. Today we are going to talk about Gaussian mixture model and expectation maximization algorithm. So here is the motivation of Gaussian mixture model. Let's first take the 1D case. In this one-dimensional space, we have some points here and another set of points here. So if we are asked to use one single Gaussian to model this bunch of data points, arguably the most proper one is like this. Right? But this model is problematic because look at here. There is no points here, which means that the density here is really low. But you put a really high density here, use one single Gaussian. So the idea is, instead of using one Gaussian, we can put two Gaussians here. One Gaussian for the points on the left, and another Gaussian for the points on the right. This makes more sense, right? For the region where the density is where has a lot of points, we put a high density here, and for the region no points, we put a low density here. So we can find a way to combine these two Gaussians into a valid distribution. This is the Gaussian mixture model. So here on the slides, I have another example, which is on the 2D case. You can see that we have two clusters. So if we are going to use one two-dimensional Gaussian to model this, the problem is still that you put a high density on the center, but the density there is really low because there are not too many points. This is the 3D view of a Gaussian density function, and that one is a bird view, meaning that you look at this Gaussian from the top view. And you will see a center of concentric contours. And points near to the center will have a high density, and points far from the center will have a low density. So the solution is, again, instead of using one single Gaussian, we use two Gaussians for each of the two clusters, and find a way to combine them. This is basically the motivation of Gaussian mixture model, and here is the formulation. We have a center of points xi 1 to n, and we assume that there are k clusters in this center of points. And for each of the cluster k, small k, we are going to use a Gaussian. We are going to use a multivariate Gaussian distribution to model the points in this cluster, which is normal distribution x, parameterized mu k. Mu k is the mean of this Gaussian, and sigma k is covariance. Now we made an assumption that for each of the point xi, we have an indicator zi. Zi is a multi-nominal variable which can take the value from 1 to k. So if Zi equals to 3, means that this point xi is coming from the third cluster. If Zi is from, say, 5, point x is from cluster 5. Another assumption we made is that, look at this example. We have 3 clusters here. Now I ask a question. How likely a point, an arbitrary point x, is from this cluster 1? The probability could be high, right? Because this cluster is really large compared with these 2. So we can see probably 70% with a probability 0.7, a point is from cluster 1. And these 2 are small, so we can, but their size is almost the same. So we can probably put an equal probability over them, say 0.15, 0.15. This is called the prior information about this cluster. Without observing the data point, you can somehow have a guess how likely this point is belonging to a cluster, simply based on how large this cluster is. So this is the prior probability. Again, for each of the K cluster, we have for cluster K, we have a prior probability pi k, which means how likely I'm going to use this, how likely I'm going to assume a new point is comes from this cluster. Remember that the meaning of Zi is indicates which cluster this point is from. So the probability Zi equals to k, that is the probability that data point xi is from cluster k, equals to the prior of this cluster, pi k. Given this setup, we are going to derive the distribution of a Gaussian mixture model. So give a point x, the probability under the Gaussian mixture model is Px, which equals to right. Px is the joint probability. So we marginalize Z out, we get the marginal probability of x. Now we factorize this joint probability into Px, Z, Pz, according to the product rule. Because Z can take the value from 1 to k, so we can explicitly write this out. K equals to 1 to capital K, and Px Z equals to K, Pz equals to K. According to our setup, this probability Px given Z equals to K is if I assume that x is from cluster K, so what's the probability of observing Px? This is simply the probability mu k sigma k. We use the Gaussian distribution associated with cluster K to model this data point x. And the pz equals to k is the prior probability of choosing this cluster K. And this is K from 1 to capital K. We are done. So this equation is the density function of a Gaussian mixture model. So Gaussian mixture model is essentially a distribution, and its density looks like this. Notice that pi k greater or equal to 0 and less equal to 1. And their sum equals to 1. Remember that pi k, the meaning of pi k is the prior probability of choosing a cluster. So we have capital K cluster here, so their sum must be 1. And each of the component pi small k must lie in 0 to 1. So from this, from the density function of Gaussian mixture model, this equation, you can understand why this model is called mixture of Gaussians, because each of the pi k is a number from 0 to 1, and you multiply it with a certain Gaussian and do the sum over all the products. So we are using the center of pi k's to mixture this center of capital K Gaussian distributions. This guy is taking a convex combination of a center of Gaussians. That's why it is called mixture. And as we said, Gaussian mixture model is simply a distribution. For example, in this example, we have 3 single Gaussians denoted by the blue curves. If you mixture them with 3 pi k's, and we'll give you a mixtured distribution denoted by the red curve. And this is the 2D case. We have 3 Gaussians. The red one, the green one, and the blue one. If we take the mixture of them and the weights of the Gaussians are 0.5, 0.3, and 0.2, and finally we get a mixtured distribution like that, like the purple curve. So this is basically the Gaussian mixture model, a distribution, which is mixtured from a center of single Gaussians. And the mixture will allow us to give us more flexibility to describe the data we have. So any questions here? Example of Gaussian mixture model? Applications? They can be used for clustering, right? Domain. What do you mean by domain? For example, in speech recognition, they basically use a model which couples a Hayden-Markov model and a Gaussian mixture model. So for each of the hidden states, it assumes that it is combined from from k single Gaussians. So So suppose this is a Heidelberg-Markov model used for speech recognition. And suppose these latent variables denotes the phonemes. And each phonemes can correspond to essential features. But these features can exhibit clustering characteristics. So for this guy, Z2, it can have let's say 3 components. And when I observe X2 from Z2, I'm going to model X2. Using a Gaussian mixture model related with Z2. So if you assume that in your data there are some clusters, there are multiple modes of the distribution of the data, you want to use a Gaussian mixture model to model them. That is completely different. The Gaussian kernel simply use the Gaussian function. Yeah. In kernel methods, the Gaussian kernel is used to measure how similar two points are. This Gaussian mixture model models the distribution of essential points of a population. So they are different things. Any other questions? So given this model, the next thing is how to learn it. We have a set of parameters in this model. For each of the cluster or the component, we have each component is a Gaussian. It has a mean vector and a covariance matrix, and the clusters also have priors. So we want to learn these parameters from data. Of course, one thing you can do is use maximum likelihood estimation. We know that given a point x, under a Gaussian mixture model, the density function is so now have a data set D, which contains n points. And we can define a likelihood over the data set. Right. This is a function with respect to pi k, mu k, and sigma k. So you take the so you maximize this function. It will give you the value of pi k, mu k, and sigma k. However, this is very hard. Let's take a naive try. Usually we maximize the log likelihood PD. So PD equals to I equals to 1 n log naively we can try to maximize this function to get the value of the parameters. However, this is very hard because if you take the derivative of log, the whole term, the sum term there will comes to the denominator. to the numerator. Yeah. Let's try phi log PD. Let's say we are interested in pi k, so we take the derivative pi k. I equals to 1. This would be you will have a derivative of pi k, something really complicated like this. And in this equation, suppose let's say you send this derivative to 0, and in this equation the parameters mu k, pi k are coupled. Basically, there you will get and at the end of the day you will get a set of nonlinear equations. There is no analytical solutions to that. So that's why we don't do the MLE estimation directly from this density function.
We don't do this because it's too difficult to
Because it's too difficult. You take the derivative with respect to pi k, mu k, and sigma k, and send them to 0. You will have a set of equations, right? And think about the equations. This is a unknown variable, and these two are also unknown, and these two. And this set of equations are really hard to solve. Normalization? This one? No, this is the derivative of log. You take the, right. So instead, we can use a method, as you know, expectation maximization to solve this problem. So EM algorithm, basically it is a mathematical trick which will decouple these parameters and makes the learning easier. So before proceeding to EM, let's first clarify some definitions. The first one is input data. Input data is the data you observed. In this example, it's the points you observed, right? Each point might have a feature vector. And actually, all you observed is this set of x. The second definition, the second thing is local variables. Local variables in the Gaussian mixture, in the Gmm Em case, they are the z's. Remember that for each of the point xi, we associate a zi. Zi denotes which cluster this point belongs to. So each point xi has something zi, and this zi is called local variables. They are local because they are only associated with a single point xi. Say if I have 2 points x1 and x2, x1 has z1 and x2 has z2. Z1 has nothing to do with x2. It is local to x1. So that's why they call the local variables.
Why do we construct such local variables if they know which cluster the xi belongs to?
Firstly, conceptually it is easy to understand, and secondly, later you will see in the EM algorithm, this latent variable will make our optimization problem much easier. So the third thing is global model parameters or global parameters. In this model, it is pi case. mu case and sigma case. These guys are called model parameters because each point xi will use the pi k, mu k, and the sigma case to model themselves. They are related with every points we observed, so they are called local. So they are called global. To estimate the local variables, the procedure is called inference. To estimate the model parameters, the procedure is called learning. So inference and learning are basically the method you are using to estimate the unknown variables. If you are trying to estimate the local variables, the procedure is called inference. Otherwise, it is called learning. Now let's derive the EM algorithm. So basically, the learning principle is still the same. We are trying to give a set of points. We want to learn the parameters by maximizing the likelihood defined over the data set. For simplicity, let's simply take one point x, and you can easily generate two multiple points. So we have a single point x here, and the likelihood defined over it is px, and we want to maximize the log likelihood to estimate the parameters pi, mu, and sigma k. If you put the this density function into here, as we analyzed before, it's very hard to solve that problem. So we are going to play a trick here. Px, by definition, is right. We have a joint distribution of x and z. So we sum out z, we get the marginal probability of x. And z, remember that it denotes which cluster x belongs to. So here comes to this important trick. We multiply something, qz, and then divide it. The equality still holds, right? It doesn't change anything. We multiply something and divide it.
It must not be zero, right?
Yeah, we assume that. And look at this term. What is this? This is the qz is, by the way, qz is a distribution over z. It could be any distribution you want, uniform, Gaussian, or some unknown distributions. And this equality here holds for all the possible choices of qz. And now look at this term. What is this? We have a function defined over z, and here is a distribution. And here we do the summation. This is simply the definition of expectation, right? We use a notation EQ, expectation with respect to Q, PXZ, QZ. And the notation here, EQFX, means EQZ, let's say Z. Integration of QZ, FZ, DZ. Or if Z is discrete, the summation QZ, FZ. Any questions so far? Yes.